Let's talk about cross-validation for classifications for a bit. Well, up to now, we've learned classification method with only one logistic regression, right? Well, I will introduce you to K nearest neighbor classification right after this, so that you have something to for comparison. Okay, so for the cross-validation, we did it in the regression setting where we used the mean squared error to quantify the testing error to compare models, right? Well, to use it in the classification setting, all we need is to consider the number of misclassified observations. That's our error, right? For in the classification setting. With leave one out cross-validation, the classification error rate will be, you can write it like this, the cross-validation error equal to the averaged error, like for each, for taking each of your observation out and evaluate, train your model with the rest, with your n-1 model, and then checking the misclassification error, like basically for that single observation that you treat it as your testing set, you just see if it's misspecified or it's correctly classified. Well, just count how many errors you made for those single testing observations and sum them up, divided by n, that's your averaged misclassification error. Okay, so basically this is just right in the indicator. This I is an indicator of any of the predicted yi, which is yi hat. If it's not equal to the observed value yi, then that's an error, right? You just count how many error you made, sum them up, divided by n. Okay, so this is the classification error. For leave one out cross-validation. Well, yeah, as I said, I'll introduce this K nearest neighbors for this is the very simple classification method, and it's definitely need use cross-validation, so that's why I introduced it here. So yeah, let's take a look at what it is. So K nearest neighbors, we will write KNN in short. So KNN estimates the conditional probability of a class given the data by just looking at the neighbors of that data. So just by looking at the neighbor of the data, we will determine like which class it should belong. And it's a non-parametric classifier because there's no like betas to estimate. So in our regression setting, we have those coefficients beta 0, beta 1, beta 2, that intercept and slope. Those are parameters that we will estimate in the model. Well, this KNN, it's a non-parametric classifier. There's no such parameter involved. Well, we only need one thing, the K, which is the number of neighbors you will look when you determine the class for your testing data. Well, given a test observation x0 and an integer k, so this is the number of neighbors you look, k. Well, the classifier, the KNN, will identify the k nearest points to x0 and counts the number of them in each group. And the test observation is predicted to be the classification type that has the most numbers near. Okay, so we have this test observation x0. We will take k of its nearest points. So basically find k neighbors to this x0, and we count what the most of those k neighbors belong to. Then we will just predict the test observation x0 to be that class. Let's take a look at example here. Well, this is strange. Let me take a look what happens to my, yeah, this is strange. Well, never mind. Let's just use this version of the plots. Okay, so this is an example for the KNN when we take k equal to 3. So basically we find, so this is our x0. That's our testing observation testing point. So that's a new point at this x. And the KNN would look for the nearest 3 neighbors, like this one, and this one. And assign this x to blue, because we have 2 of the neighbors being blue and 1 of the neighbors belong to yellow, or yellow. So we will determine this new data points x should be blue. So this is how we use k nearest neighbor. And if we do this for all new points, like if we do like a boundary, if we do a grade of data points of this x, like a grade just like this, like each of the single data points, if we do this over a grade, we will find the boundary for the yellow and blue region. So this picture on this right is the decision boundary, visualizing where the model would predict a yellow or blue for new data points. So this is like doing prediction on a grade, then you can draw like where the boundary is between the blue region and the yellow region. Okay, so this is just an example of KNN with k equal to 3. And we can also like increase the number k. If we use k equal to 10, we will get a boundary like this. Well, this is a much larger data set we have. Okay, so we have much more data points, like those yellow and blue circles. That's our observations. That's the data we have, and we are using the data to draw a boundary, to distinguish, to classify for a given observation if it's yellow or it's blue. So in this plot, the dashed purple line is the decision boundary. So that's the true underlying boundary. Well, it is from the Bayes classifier. Well, we will not talk about this Bayes classifier. You can just think it as the unattainable gold standard. So you can think it as the underlying true or close to the true boundary of the underlying model. Okay. And you can read more about this Bayes classifier on this textbook, Introduction to Statistical Linear Regression. introduction to statistical linear regression with R, linear model with R, whichever. So yeah, this is the best or the close to the truth boundary, and this black line, black curve is the decision boundary with k equal to 10 with a KNN classifier. Okay, it's fairly close. And you can actually see there is a few yellow points on the blue side, right? And also there is a few blue on the yellow side, but overall, it's already a good classifier, close enough to the to the golden standard classifier we have here, the purple line. Okay, so well, I'm going to show you like how like do we determine the flexibility of a KNN. Well, this is like we use two extreme cases. One case is to use k equal to 1. Basically, we will only take one neighbor and to say if this neighbor, if the neighbor of the x0, like the new data points, if it's blue, we will see this x0 should be blue. If its nearest neighbor being yellow, we will see this new data point x0 should be yellow. So that's when k equal to 1. And this black curve is the decision boundary with k equal to 1. If we use k equal to 100, and this boundary is essentially become almost a straight line if you take a look here. So, well, this k determines the flexibility of your classifier, and you should really choose the k very carefully. And the more flexible, like this is like way too flexible. Like this will lead to overfitting for sure. And for this one, it's not really good, right? When you use too many, we use too many of the neighbors to do this KNN. The model, like the prediction error, definitely not good in this case. But this one is way too flexible. You are overfitting the data. So for KNN, it's very important to choose the correct level of flexibility. So basically choose how many neighbors you would use. Yeah, we will do a cross-validation for it in a second. I will show directly to you the result. And for now, let's take a look. What if we use polynomial logistic regression to do this classification? Well, because with regular, like with the simple logistic regression, it would only give us like a straight line sort of. And we want to build a relatively flexible model, like we want a curve. So we increase, so we increase the number of polynomials in the equation here. So originally it's just these two terms being our straight line. And now we have polynomials, like the quadratic term in this example. And it's just like polynomial regression. You just add more and more polynomial terms for the logic response. And the decision boundary for linear, so this is the linear, and quadratic, so when you adding these quadratic terms, and cubic, when you add furthermore like the cubic terms, and quartic. So that's the force power of the axis. These four are shown here. So this is for linear, quadratic, cubic, quartic, polynomial, logistic regression. And the test error is provided by the book. The test error rates correspondingly are around 0.2 for this two, and these two are around 0.16. And if we compare this to a base error rate, like this is the base error rate, almost the truth, but not exactly. So it has an error rate of 0.133. So for sure this is not as good as this, but these two, like this cubic and quartic, they're already good enough. Well, for KNN, well, oh yeah, no, not that point yet. So how are we supposed to choose? So in the polynomial logistic regression, how are we supposed to choose how many polynomial terms we should include, like the power of the polynomials? So we have the result of the cross-validation. So we actually made a plot with comparing the tenfold cross-validation error rate and the true test error rate, which is the brown curve. The true test error rate is, you can think that's the base error rate, and oops. Yeah, and the blue curve is the training error. So basically, this is the training error, blue curve, and this is the tenfold cross-validation error for the black, and the brown curve is the true test error rate. So, well, the tenfold cross-validation underestimates the true test error because we just used we didn't use the full data set. Okay. But it does a good job of mimicking the shape and finding the optimal polynomial order. So use this test error, yeah, tenfold cross-validation error rate. We will find we should use a polynomial of up to 4, like we should use quartic level of the polynomials. And it's quite close, oops, to the true test error rate. Okay, and yeah, this is for the KNN. Well, it has like the same notation. Black curve is for the tenfold cross-validation error, and the brown is the true test error. I think this true test error is not from the base classifier. Yeah, this used the full data set. Well, I need to take a look at the book again. Should make this clearer. Well, this is just like a guideline that we are trying to attain because this is true test error. Again, this black curve being tenfold cross-validation error, it's fairly close to this, not exactly the same, but it's mimicking the shape and the trend of this true test error curve. Okay, and this training error is not really usable because like the more the higher, well, this is the lower k. Well, this is on the x-axis is the 1 over k. So the further it go to the right, it will basically decrease the K, like use less and less neighbors to make the decision. So that way we will get very much close to overfitting if we use the training error. Okay, we'll look at this black curve, the cross-validation error. It will give us the best model we should use, like the best K we should use for the KNN. Okay, and let's to the R lab. Yes, let me make sure. Okay. Okay, yeah. Okay, we have a short lab for the classification cross-validation. Oh, well, I forgot to mention, like when we do the regression cross-validation, well, here when we extracted the mean squared error, we have this, we use the first element in delta, because there are actually two values in the delta. One, well, the first one, which we're using here, the delta, the first delta in the cross-validation result is a standard estimate, and the second is the bias corrected. And you can actually, yes, of this delta, so in this help file, so I got this with question mark cv.glm, and then you will be able to find like what are the arguments, and oops, yeah. Well, those are the arguments, and this is from the output. So we extract the delta from the output of this function cv.glm, and it told you here it has a vector of length 2. So we just used the first component, which is a raw cross-validation estimate of the prediction error. And the second component is the adjusted cross-validation estimates, where the adjustment is designed to compensate for the bias introduced by not using leave one out cross-validation. Okay, so when we use this 10-fold, like K-fold, it has this option where you can use adjusted cross-validation estimate. But for here, we just use the raw, the standard estimate of the prediction error. Okay, I just forgot to mention this. Oh, and also we said the leave one out cross-validation would take more time. So this is the code that I used to check the timing for, this is for the leave one out classification, cross-validation, and this is for the K-folds, well, basically 10-folds cross-validation. Well, this first one will take more time. I just didn't run it when we talk about this cross-validation for regression. Well, that's it for the previous part, and let's go to the cross-validation for classification. Okay. Well, I got this example from here. Okay. Well, basically, it's well, you can definitely take a look at of this website. Well, it has many materials on like data analytics, and this is specifically for cross-validation with KNN. I find this is a great example, so I just used it here, and here is the reference. And the objective for this data is to we want to predict whether a worker will have raw wage about 100 or not. So it is a classification problem, okay? So whether it's about 100 or not. So here it did some pre-processing of the data. Only white data is considered for prediction. And because there is some binary variable and ordinal variable, like it's like have 5 levels with different order. So this education variable, and it has some pre-processing here, and age and year are assumed continuously. Okay, let's take a look what the data looks like. So here in this data set, wage, you have year, age, and for education is ordinal with 5 levels, and this drop class is binary. Okay, industrial and information. And here, basically, we first like only use race equal to white. So we will only use this subset of data for this example. And we convert this education into binary, 0 or 1. So this as integer will set this 2-level factor into integers to be 0 or 1. Let's just run this and you will see what the data looks like. So if we do data, see, oh, sorry. So as integer, we'll convert this factor into 1, 2 instead of 0 or 1. Okay, so we'll just use we just kind of reset them, set them to numerical data. And we use this data set to do our example. So first, we did this training and validation data set with half and half. So this is sample from the number of rows of this data set, and just resampling half of them with no replacement. And again, it sets C's so that when you run this data set, when you run this code, you will get the same sample, the same result for the following. So we find this is the training data set indices, and the testing data set indices would be minus this training indices. Okay, so this is the training for this data. This is our X value. Yeah, this is our X values. So in this data. So this is the training data for all the X's, and this is the testing data set with for all the X, the predictors. Okay, and the training wage, which is the training set for Y. So Y is the thing that we want to predict it. That's whether the wage is greater or less than 100. Okay, and this is for the training Y. And M equal to 50, that's the, well, let me see. Oh, yeah, that's the neighbors up to 50 neighbors we want to test on. Okay, so we will do this in a loop, just as we did previously. So this is the function for KNN, and this KNN function is from this package class. So you have to load this package first in order to use this KNN, where you just need the training set, the predictors for training set, predictors X for the testing set, and the response for training, and also specify the neighbors you want to use, number of neighbors you want to use for the KNN. Okay, and you record the errors for each for each different I values. Yeah, this is the testing error. And also for comparison, it also record the training error. Like basically you use the training wage. This is the error term on the training data set. Okay, so let's run this from here. Let's run this. So this loop takes a little bit of time, and let's make a data frame. Use this training error and test error. That's just prepare for the following plot. Okay, so this is make a data frame with this column. Well, let me just show you what this data frame look like. That might be easier to tell. So apparently the name is given from here, like the column names is given here. And here, the columns, I'm using this like training with 1, 2, 3, 4 up to M, which is 50. So, wow, okay, I need to show you what this is, just in case you don't know what I'm doing. So this is a vector with like, oops, oh yeah. So this is the vector with first the 50 being training and the last 50 being testing. And this K is from 1 to M for the training, and then from 1 to M for the testing as well. Okay, and then combined with this training and testing error that I just calculated here. Okay, maybe it's easier to look this way. So I have this first column is this thing, okay? And if you look, we have 50, like training 50, and then start testing 1 up to testing 50. And then I also combined the training error and testing error into one long vector. Okay, so it's a long vector of like 50 plus 50, that's 100 data points. So I made this a data frame like this so that I can use this plotting function from ggplot2. So this way I can like get like the legend automatically by this group and color. Okay. And this is the training error and testing error with half and half split, because I only like sampled 50% of the rows for training, right? And you can tell like the training error rate will increase when we use more and more more and more neighbors for the KNN. And when we use k equal to 1, remember we will definitely have overfitting. And the error is really low when k is small and for the training set, and it's really high for the testing set, which is not a good choice. Okay, and we want to minimize the testing error rate. Okay, and this training is just for comparison. Okay, this is training and testing split for this KNN, and it also has example with leave one out cross validation. Well, this leave one out cross validation is done for yeah, with this function. So like KNN dot CV. Okay, so yeah, and I think I might forget. I think I run this, but this is the library, the package that has this function. You have to first install it if you have never used it before. Okay, before you can load it and run this function, and initiate error vector of length m to store the cross-validation errors, and then calculate the cross-validation error. Well, this is leave one out, so by default. And this is again, you specify the neighbors you want to take for the leave one out cross-validation. Let's run this. Take some time, and we will make a data frame again. And this data frame looks like this. So this is a number of k. Well, I only record, only saved the testing rate. Yeah, testing error rate. So that's why you only see one error rate here. Okay. And let's make a plot. Yeah, this is the leave one out cross-validation error. Then you can choose the best k. Right? Like for testing error, the smaller k you have, the larger the error will be. So you have to find the right k, like looks like k equal to 24 will give us the lowest testing error. Okay, so this is a small illustration of cross-validation for classification, like the KNN. For the logistic regression cross-validation, you can refer to the textbook, ISLR. It has more details on it. So this is just for the KNN. And that concludes the cross-validation for classification. Okay.